right, we have a bit to do, so let's dive right into vectors. First of all, what is a vector? A vector is something that has magnitude as well as direction and obeys the rules for combining vectors. This kind of nonsense comes up all the time in math. You get a thing, it's like a thing is a thing that obeys the rules for being a thing. It's like, oh, that's helpful. So we're going to talk about the rules for combining vectors for a while, but before we get into that, let's think of what we're talking about, what kind of things we're used to thinking of as vector quantities. For now, the alternative to a vector is a scalar. A scalar is going to have only magnitude. So you may be able to think of a couple of these off the top of your head, and if you think them really hard, I'm sure I'll be able to pick up on them through the wonders of the interwebs. Splendid. You were thinking of time, temperature, probably pressure, maybe. Yeah, maybe you're thinking of speed. Speed, I think I got there a little bit. Distance, I feel like I heard a faint echo of. All of these are things that simply have a magnitude. They don't have a direction associated with them. We think about an arrow of time, but mathematically we tend to ignore it. Temperature, it's not 27 degrees up or negative 36 degrees south by southwest. Speed and distance, though, we may think of, speed, we talk about velocity as speed in a given direction. And that tells us that velocity is a vector. Displacement we think of as distance in a given direction. No one ever says that out loud, but displacement, we do have to care about what direction you're moving in, not just how far you moved. Similarly, acceleration is going to be a vector quantity. We think of that from how we can be speeding up or slowing down. We know we can be accelerating in the direction of velocity or not. Other exciting things, various fields are going to be vector quantities. That's always thrilling. And stuff like, I'm not going to put torque. Torque is technically a pseudo-vector. It's weird. Not everything are scalars and vectors. There are things beyond this. I just alluded to pseudo-vectors, which do not transform like vectors, it turns out. They don't obey all the same rules. They do a weird thing under inversions. They pick up a minus sign. It drives people upset. It makes people upset. It makes me upset. Minus signs, I have an issue with those. One more step up the ladder, you get tensors. The most notable of these is probably the stress-strain tensor, which cares not just about if it's in the x direction or not, but it's an ordered matrix, so it cares what it looks like: xx, xy, xz. You get some weird stuff going on with that. Also, the curvature tensor is kind of a big one for general relativity, and that's complicated. All right. Now, since we've been talking about things as having magnitude and directions, it's useful to think of them as arrows. Arrows kind of capture our whole magnitude direction business without too much fuss. You're looking at a situation where you clearly have something pointing in a given direction, and all right, that was weird. And has a given size. We can talk about this thing. Oops. Having some angle above the horizontal, and it can have some length. When we talk about these things, we'll talk about sometimes the magnitude of a vector. It will sometimes be written this way. It will sometimes be written this way. It will sometimes be written this way. Be careful not to confuse this one in particular with someone just forgetting to put an arrow on top of it. The arrow, by the way, indicates that it is a vector quantity. Now, that's all well and good, but we want to be able to do some work with these. So one thing we want to be able to do is add vectors. So let's grab this and grab this, and I want to know, what is a plus b? So I've kind of alluded to it. A plus b, if I start here, I'm going to go in the direction of A, takes me to this point. I'm going to go in the direction of B, takes me to this point. This resulting vector here is my vector A plus my vector B. This is the same idea, if you walk west for 3 blocks, you walk north for 2 blocks. This is the same kind of situation that you're looking at. Your final displacement as the crow flies, or the raven flies, or the morning dove whatever. So bird flies. Just takes from initial to final. So if you're thinking of this as displacements, displacement 1 plus displacement 2 is just your total displacement. This kind of makes sense graphically. I think there's a strong intuitive argument for it, but the problem then becomes, how do we start to do this more analytically? If I haven't just drawn out pictures of arrows, or if I have drawn pictures of arrows, but I care very much about how precisely they are, I want to be able to rely on better than, trying to get down to the 10th of a degree when I'm drawing these things to make sure everything's pointing in the right direction. So in order to look at it more analytically, we want to include a coordinate system. So let's say that I've got here A, my good old vector, and this pretty bog standard XY Cartesian coordinate system. If I drag A into this thing, this horrible mess, I don't need this anymore. What I'm going to discover is that there is some of A pointing in the X direction, and there is some of A, wow, hold on. I'm really bad at setting things up. Thank you. There we go. Some of A pointing in the X direction, some of A pointing in the Y direction. So here's my vector A, and I'm going to say A has two components, AX and AY. And I can see, looking at this, that A equals AX plus AY. These, we will say, are the vector components of A. At this point, it might be interesting, although not terribly illuminating, I assume, to point out I could have done anything. I could have said these were my X and Y axes. Here's X prime, Y prime. A now has an X prime coordinate, and it has no Y coordinate. This is also true. We're going to come back to this idea at some point. The idea of rotations and projections is very much a physical idea. It's not huge for us in this class. It'll come up every once in a while, but it's worth keeping in the back of your heads that, just because we have a standard up, down, left, right coordinate system doesn't mean the world is up, down, left, right. That is something we chose as a viewpoint to look at it. Every other viewpoint pretty much equally valid as long as you can, transition from one to the other. Now, this should be something that we are familiar with. As I look at this shape, I'm like, oh my goodness, it's a right triangle. If I know this angle, I know that the x component, the length of AX, you notice I'm not drawing my arrow, is A cos theta. Because cos theta is AX over A, the length of these sides. Similarly, AY is A sine theta. Be careful. A particularly devious textbook, AP exam, whatever, could instead use phi, this angle. This is going to happen all the time in some problems where you're talking about angles of descent instead of angles of ascent, below a horizontal instead of above a horizontal. In that case, this would be true. The reason I bring this up is because it is better to make your triangle, your reference triangle here, and draw the stuff out and check it than it is to just always assume x is cos, y is sine. Do not get into that trap. If you buy into that, the second that something weird happens, you're just going to have everything backwards and it's going to make your life miserable. All right, so moving on. We can now talk about a vector in terms of these components. So we had said, refresher from 3 seconds ago, the vector A, in terms of its vector components, is AX plus AY. Incidentally, we could expand this just as, nope, not talking about multiplication yet, just as easily to include, nope, not talking about that yet, AZ, but that just complicates things and makes us draw everything many more times than we need to right now. So we're just going to stick to X and Y. So we're going to make things a little more complicated to make them a little simpler in the long run. I've taken, again, these vector components, ax, ay, and I've broken them down one more time so that I now have these scalar components, ax and ay, just numbers. And then I have these unit vectors, I hat, j hat, or as I'm probably going to call them 90% of the time, x hat and y hat. Well, I hat and j hat have a certain charm. A unit vector only has a well, doesn't only have a direction. It has unit length. Unit in this case like unit circle. So a length of 1. So basically only has a direction. So x hat is the vector that points in the positive x direction. It has length 1, points in positive x. Y hat, length 1, points in positive y. I hat, j hat, respectively the same thing. So now, if we take this one step further, we can see that two vectors are equal if and only if their components are equal. If I take a look at, going back to this A plus B endeavor that we had going a while ago, equals, let's call this now C. I can tell that A looks like AX, X hat, plus AY, Y hat. B equals BX, X hat, plus BY, Y hat. If I add these things up, I would see that A plus B looks like AX plus BX, X hat, plus AY plus BY, Y hat. We're assuming a lot of stuff about adding vectors and multiplying vectors that I'm going to make slightly more explicit down the line. But even just kind of drawing this out, we would see here is, for example, there is AX, and there is BX. Here is AY, here is BY. It's one of those things, if we look at it, it looks pretty solid, and these are just kind of, we're defining this is how we carry these things out. And so this would tell us then that C, which looks like CX, X hat, plus CY, Y hat, that this has to be true. That AX plus BX is CX. The components, the equality of the components is what tells us about the equality of the vectors. All right. This is, again, kind of technical stuff, but in practice what it means is to say that a vector equation is equal means that the components of the two vectors are equal. If the components are not equal, you do not actually have equality. All right. This brings us to an interesting point, something we kind of subdued. We can have vector multiplication. We just saw examples of scalar multiplication of vectors. A vector times a scalar gives us a new vector along the same line, but possibly with different length and or direction. So we saw this up above where we had, the vector component AX was the scalar component AX times X hat. It is AX units in the X hat direction. So I have a vector C, which I can think of as CX times X hat. 1/2 C, I can think of grouping that 1/2 with the magnitude. So it's going to be half the length in the same direction. If I have minus C, I can think of this minus sign as being grouped up with the unit vector. The minus sign doesn't affect the magnitude. 4 and -4 have the same size in terms of their absolute value, if you think of magnitude that way. So that minus sign has to be impacting the direction. So this is now a vector of the same length, but in the opposite direction. So this stuff, not too bad. I find this is a particularly useful way of doing vector addition, or rather vector subtraction. I think of A minus B as A plus the opposite of B. I never have to remember all the weird head-to-tail stuff that they talk about in textbooks when they do this. Minus sign's the devil. Subtraction, still on fuzzy ground. All right, this is where it's going to get worse. We're not going to use a lot of these things physically for a little while yet, but we got to start introducing it. If you have vector times a vector, specifically vector dotted into a vector, the fact that it's a dot and not a cross here for multiplication matters. This gives a scalar which indicates the amount of one vector pointing in the direction of another. We've actually already seen a little bit of this, but we're going to come back and formalize it here. This is called the dot product or the scalar product. Scalar product because it returns a scalar, dot product because it's represented by a dot. We're going to define the dot product to be a dot b as magnitude of a, magnitude of b, cosine of phi. Phi is the angle measured between a and b. So if I have a, I have b, this is the phi that I'm talking about. This projected amount is useful in a lot of cases. We actually made use of it before to find the scalar components of these vectors, in a sense. The scalar component of a is the amount of a in the x direction. So the scalar component of, or the x component of a. So if I have s, some vector, I dot it into x hat, my unit vector, in the x direction, I should get the x component of s. If I look at this, I'm going to get the magnitude of s times the magnitude of x hat, which remember is a unit vector, so it has magnitude 1, times the cosine of the angle between them. So I get s cos phi, exactly as I expect if I wanted the x component of it for a standard right-handed coordinate system in the usual sense. Physically, we're going to see this come up in terms of work. That is probably going to be the most prominent example of this, where you only care about the force that is exerted in the direction of the displacement. So taking the dot product of those tells you how much work is actually being done. This is why technically if you are just carrying an object from place to place without lifting it, you don't do work, although your muscles still hurt after a while. A couple things to note. Since cosine of 90 is 0, the dot product of perpendicular vectors is 0. And this allows us an alternate expression. I'm not going to go out and do this, but you can FOIL vectors just as though they were regular numbers. So if I go and do all of the multiplication through this thing, any term that looks like x dot y or y dot z or z dot x or any combination of those, they're all 0. The only things that you get that you're left with are things like x dot x or x hat dot x hat, which we would know is the magnitude of x hat, which is 1, times the magnitude of x hat, which is 1, times the cosine of 0, which is 1. So it's just 1, which would give us then ax bx times x hat dot x hat, ay by times y hat dot y hat, az bz times z hat dot z hat, or ax bx plus ay by plus az bz. Someday down the line, you may see this written in this awesome manner, the Kronecker delta ai bj, and the Kronecker delta is such that it is 0 if I does not equal j, and 1 if I equals j. And these repeated indices mean that this is to be summed over I and j from 1 to 3, as Einstein's summation convention. As you start getting into general relativity and special relativity, you wind up with these messes of equations that are massively vector or tensor based, have tons of indices, and writing summation symbols all over the place gets boring. This is just a really cool way to hide a whole bunch of stuff, and you get to write a lowercase delta, which is sweet. Anyway, one more thing. This is the other type of vector multiplication, a vector times a vector. This is going to return a third vector, which is perpendicular to the first two. This is known as the cross product or the vector product. Some weird things come up with this. We're going to see it physically when we get to rotation. So we're not going to touch it now as much because it's way down the line. This is going to come back to us. You just want to kind of look at the framework for setting this up. Physically, it's much harder to interpret this. You see it sometimes. The most common uses of this are in torques and rotation, as well as being able to find projections off of a plane or find the direction of the normal to a plane. Because if you cross two vectors that make your plane, and you can make any two vectors in that plane that are not parallel, and you've defined a plane. If you take the cross product of those, you get a vector that's perpendicular to them, so you get the normal to that plane. That comes up in some vector calculus down the line. Neither here nor there, though, right now. we define this thing to be a cross b equals c. That's our third vector. And the magnitude of c is going to be magnitude of a, magnitude of b, sine phi. Phi is, again, the angle between them, this time by shortest measure. Otherwise, you get some weird stuff if you take the long way around. The direction of c can be found by the right-hand rule. Turns out that a screencast is a miserable way to do the right-hand rule. You should consult the picture in your book. The short way to do it, using your right hand. Seriously, you'll be amazed. Put the edge of your hand along the direction of your first vector. Curl your fingers by shortest distance towards the second vector. Your thumb, when given the thumbs up sign, will indicate the direction of your third vector, or thumbs down if it's, that way, because of how you curled. There are other ways to do it. Some people do it with like index, middle, like you do weird stuff with that. I've always found point, curl, thumb to be a satisfying way of doing it. You get to get a thumbs up or a thumbs down. You feel like you're a Roman emperor. It's very, I get caught up in the moment sometimes. Do remember though, right hand rule uses your right hand. The cross product is anti-commutative, which is weird. This comes up a lot in some strange places. So A cross B is the opposite of B cross A. Also, since sine of 0 equals 0, the cross product of parallel vectors is 0. Again, we're going to come back to all of this later. For now, this is the one piece of information you need to take, is this horrifying expression. There are many ways to derive it. One of them is to take your two vectors and a row of unit vectors and make a matrix like this. And then the determinant of this matrix is this. If you expand by minors, you can see pretty quickly that you would get AY, BZ, minus BY, AZ. If you continue that expansion, so if you're up on your matrices, that's one way to do it. Another way to do it, which is significantly more elegant and thus infinitely more confusing, is this Levi-Civita tensor. I think it's a tensor. This thing is defined to be 1 if I, j, k are cyclic, -1 if I, j, k are anticyclic, and 0 if any repeated index. So what this means, let's say I wanted to know, so I have epsilon x, x, y. So that would be ax, bx, cy. That doesn't happen because this thing is just 0. All you get are terms that look like this, x, y, z, times ax, by. And again, because we're repeating these indices, we have to sum over all of them. So that means we would also catch a term that looks like yxz. This one, these are cyclic, so this is 1 times ax by. These are anticyclic, xyz, xyz. So this is -1. And so the z component of this thing should look like ax by minus bx ay. You do have to be careful. Someday when you do quantum mechanics, you think these things don't commute. Weird stuff happens. It's a little terrifying. For now, we can be a little sloppy about it. There's no reason to know this. You also don't need the other fancy definition. I just really like it. For now, this horrifying mess of an expression is something you may just have to, be able to find, or this determinant something you have to take. This is a lot of information. Most of it just definitions. Practically, we'll do like a scavenger hunt or something and kind of get our head wrapped around adding vectors and combining vectors. But for now, if you need a reference, here's your formalism. Good luck.